last but not least, let's introduce Nick. If you guys have been here before, you know Nick. He's a CPP Bay Area regular, and he also does modeling for Apple. Oh, sorry, modeling and simulation engineer. Sorry. I mean, yeah, he's a good-looking guy. I mean, you know, I wouldn't be surprised. So he does modeling and simulation engineer in Apple's circuit simulation team. He maintains Boost Math, where he wrote the quadrature, differentiation, interpolation, and statistical routines. If you know what those words are, they're probably pretty impressive. You know, I don't even know what those words are, but still sounds impressive. And he's going to be talking to us about property-based testing. I'll give it up to Nick.
So I want to talk a little bit about what people generally do to test their code. And to start off, I found this quote from Donald Knuth. He says, "The idea of unit tests appeals to me only rarely when I'm feeling my way in a totally unknown environment and need feedback about what works and what doesn't. Otherwise, lots of time is wasted on activities that I simply never need to perform or even think about." And so, do you want to start a flame war? Because I absolutely do, right? So I think DEK is right about this. I think that for the most part, unit testing is a horror show. Okay, so if you're using somebody else's unit tests, generally what happens is sometimes they just run forever. Sometimes they fail randomly. Sometimes they verify wrong behavior. Then you get things where like you don't know why the test is passing. It looks like it might be okay, but you're not sure that that's something, whether it's fundamental or incidental. There's also huge binary files that people read, and other times they just like say fail. Okay, so this is something that's a waste of time. I think Donald Knuth is right there. So if we're going to do it, I think we need some sort of opinionated philosophy about why we're doing it. And so I'm going to show you my reason why we do it. And my reason is unit testing is our current best mechanism of transmitting information about the probability of correct operation of the code between team members and through time. Okay, so this is kind of a weak definition. This is saying that this is what we know how to do. I'm not saying that people in 500 years will be doing unit testing. I'm not sure how that will happen. And it's fundamentally collaborative, right? Actually, I find that when I'm not programming in teams, there's not as much necessity to do unit testing. Okay, so there's this idea of Almond disagreement theory. So Bayesian agents with common priors can never agree to disagree. If their opinions about any topic are common knowledge, then those opinions must be equal. For two agents with common prior to agree with an epsilon about the expectation of an O1 variable with high probability over their prior, it suffices for them to exchange O of 1 over epsilon squared bits. And so this is how I think about unit testing systems. Of course, I fundamentally regard these as communication systems. My prior is that nobody else's code works. Then they transmit a few bits to me, and they don't have to, transmit a ton of them. They have a little script that shows me a bunch of green lights on my screen. And if they all stay green, then I'm like, oh, well, he believes that these are correct, and he's presenting me a few bits of evidence here. And so eventually I just kind of go, okay, it looks like this is basically correct relative to however much the original author thought it was correct. Okay, and so at this point you encounter a kind of key question, which is how do you communicate the most amount of information about the correctness of your code with the least amount of extraneous code and computation? Okay, so I want to start off with this one. Is this a good test? Okay, we got a lot of no's. Why is this a bad test? I'm gonna tell you a secret. This is one of my interview questions. I don't want to tell you how many people die on this one, but is this fair? Like, is this fair? I think it's kind of a fair question. Yeah, it tells us nothing, right? Like this number, right? This number is 0.932039, right? We don't know why it's right. We don't know what sign does from this. We're pretty much in the dark, right? So we don't know if the test fails, is the test wrong or is the code wrong? We don't get any information about that. So in my view, this test transmits 0 bits of information about the correctness of sign, right? If anybody thinks evaluating sign is trivial, these things are still being improved to this day. So our definition is a property is something we expect to hold for all valid inputs to a program. And so here is a property-based test for stood sign. So first thing I do is I sample X from some double precision number from some distribution. And I say, what do we know about sign? We know it's an odd function, okay? And if that fails, then I print exactly the value that caused it to fail. We know that it's bounded between -1 and 1. And we know that sine squared plus cosine squared is equal to 1, okay? So I hope you think this is a good test. Because if you don't, I have no good answer for you. So the test is obviously correct. This is something that Richard informed me a few weeks ago, and I was like, yes, this is clearly right. The test prints the requisite metadata to fix the problem should it fail, right? And the test executes in under a microsecond, right? So a call to stood sign is like a nanosecond, 5 nanoseconds. So I think we're a couple orders of magnitude under a microsecond. But we had to know something about stood sign, which is exactly correct. So property-based testing forces us to develop a theory of our own code. So the developer is forced to think about what the code should do at a high level rather than grunt out a few unmotivated test cases. Okay? And so after seeing this, who could tell me a property-based test for stood reverse? Next. Max said, if you reverse something twice, it should be the same thing coming back. Okay. So here is a, this is in Google test syntax here. And so what I do is I take my random device, I create a random vector, I reverse it again. You can see that I have this auto u equals v, which copies the vector. And then I just go through and validate that it's exactly the same. Yep. That's assuming somebody wrote the iterator correct. I can write a stood reverse that just deletes that whole thing, right? I can. I could implement stood reverse, and I could just do stood reverse. Do I have the pointer to the front? If I have a pointer, I can do whatever I want, right? I passed v.begin. Right, but I didn't actually pass it by, I didn't pass it by const, right? So I can just move the pointers. Yeah, the editor can hold the pointer back, right? No, I don't think so either. Okay. Okay. That is a more interesting. Yeah, that is correct. the yes. Yeah. Yeah, so some guy said something that was an obviously correct counterexample to this test, and therefore I am not going to say it out loud. I'm sorry. No, Richard's exactly right. So this doesn't actually prove that reverse works, right? This is a piece of evidence that might suggest to you that it works. So if stood reverse was a no-op, this would be kind of tautological. I think that's Richard's contention here. And I think one thing that you could do, which would be just a constant time operation, is just assert that do it once and then assert that u dot front is equal to v dot back. Maybe I could put that in there. So for another time. But for people who are into property-based testing, there is a nice trick in Google tests that you can use, which is you can have Google test repeat a test infinitely many times using this g-test repeat equals -1, and then you can have it break on failure. So this is really, really useful. And I've been saved by this many times. So this brings me to one of people's pet peeves, where they hate tests that fail randomly, right? And all I have to say to that is just because you're a hater doesn't mean this isn't effective, okay? Failing randomly is not really the problem here, right? Randomized testing transmits novel information every run. If you just run the same test every single time, you're not getting new information. You're getting the same information, which might not probe the space of all possible inputs. The real thing that people are actually getting frustrated by is the lack of metadata required to reproduce these problems, right? And so in the Erlang world, in Erlang, people are really into property-based testing. There was a guy named Hubert who wrote a book on it. And that book I read and inspired me to give this talk to you guys. And so in that world, they say that if we do something twice and we get the same input back, that is a symmetric property. And so I personally would not use the Erlang terminology. I'd call it probably a forward and inverse operation. But it's knowing the language for these things is useful. And so you can kind of have boilerplate for forward inverse operations where you just generate random data, you get the output for the forward, you get the input, and then show that the input is the same. And so here's an exercise, like what are the common forward and inverse operations in programming? I'm worried if I call on Richard, he's gonna like devastate me with a counterexample. It's illegal. That's very good. Serialize and unserialize. That's exactly right. So that's the first example that I put on there. Compress, decompress, encrypt, decrypt. This one, shuffle and sort, is a little bit, it's not forward inverse in the mathematical sense. It's actually one to many and many to one, but it still will actually work in one direction. And then you can do like push pop, rotates, and swaps. Those are all. So these are actually like a pretty big fraction of the programming universe already. And then we could also do we can do property-based testing on anything that we decompose something and then bring it back together. Okay, so can you think of anything where we split something into sub-objects and then put them back together? Split and concat for strings, yeah. Any other ideas? Trees. Trees. What do you do with trees? Oh, that's true. Okay. Oh yeah, yeah. Okay, I think actually every subtree is a tree, and then you can like say that if you join those trees, it's got to be the original tree, right? Yeah. So here are my examples. Factoring integers, this is important in cryptography, right? So I've got to factor an integer into PQ, and then I've got to multiply it back together. This is something that you would do in numerical analysis. You take a matrix A, and then you factor it into an upper triangular matrix and a orthogonal matrix. And then you can just say, oh, this norm should be small. And then this is kind of a complicated one. Set union of set difference equals the set, right? So I don't know. Actually, I've never seen anybody use this in C++, these union set operations. I hear that they're really cool for people who, you know, are into that sort of stuff. But there's also another category of stuff, which is called idempotent operators. Okay. So if we say an operator is idempotent, if we apply it twice, and we get the same thing as if we apply it once. So if I sort a list, and then I sort it again, I should have the same list, right? So does anybody got any examples of idempotent operations in programming? That's true. Yeah, if you multiply a number by 0, and you multiply it by 0 again, you certainly are going to get 0, right? Traeger? Round, yes. So if you round like a floating point number to the nearest integer, right, and then you round it again, it's got to be the same thing, right? Yeah. Yes, that's all right. No. Yeah, there we go. I like that one. That's a special case of the identity, though, I think. Okay. So here's my list. So in computer graphics, you do this thing called clamp a lot. You say, I'm going to take a number between A and B, and I'm going to, if it's greater than B, it's going to be B. And if it's less than A, it's going to be A. So if you clamp twice at the same bounds, you get the same thing. Absolute value, negative number becomes positive, positive number unchanged. You remove a file. So like if foo.cpp doesn't exist, this doesn't complain, right? It's fine. It's like, it already doesn't exist. I've already succeeded, right? Touch of a file. This is kind of an interesting one. If the file already exists, it will still exist, right? There's no error code. But Richard pointed out to me earlier today that it's only idempotent with respect to existence of this file. It actually changes the timestamp. So, and then stood unique, where you remove all the elements of a vector that are duplicates. You apply that twice, there's no more duplicates. Okay, and so expanding on our vocabulary of property-based testing, there's a notion of modeling, where you're testing a code against a slower, obviously correct implementation. Okay, so for instance, if I have if I spend 2 weeks writing a parallel implementation of some algorithm, maybe it would make sense to test it against the serial version I wrote in a day. If I have a sparse linear solver, maybe I could test it against my dense solver for very small matrices. Or if I tape out an ASIC, right? Maybe I'll try that same algorithm in Python and make sure that it works there as well. And so this one's a big one. Has anybody heard of stood nth element? This is one you can keep in your back pocket and pull it out every now and again. So how would you test stood nth element? So stood nth element, for those people who are unaware of its operation, it basically says, find me the nth element if this was sorted, but it doesn't take n log n time, it takes O of n time. Okay. Yeah, sort it, right? So basically I've modeled stood nth element with stood sort, right? It took n log n time, but you're hoping the nth element is actually O of n. And so here's my Google test syntax for this. Just do the stood nth element. The median of that is the middle. And then you just sort it, make sure it's the same. Okay, and then there's this notion of invariance. So an invariant is something that we should always be true through a loop operation or a class or after a computation. And a lot of invariants are actually documented. You might not know this one, but if you go to CPP reference, it has a documented invariant. Okay, it says stood upper bound returns an iterator pointing to the first element in the range first last, such that value is less than element is true, or last element if no element is found. Okay, and so if you just go through that and apply that definition very carefully, this is a property-based test. And so if you can recognize idempotence, identify a forward inverse operation, synthesize a decomposition, find a model, find an invariant, then you can do property-based testing. There might be other options. I've not actually partitioned the entire space of property-based testing here, but I feel like this is a very large fraction of the computational universe, such as I experience it. And therefore, we're at 30 minutes. And therefore, I think a lot of other people, if you know this vocabulary, then you can start working in this way and hopefully be a little bit more effective. Okay. So there's a few more pieces of vocabulary that I wanted to go through, because vocabulary expands the set of ideas that we can have, right? And so in the property-based testing world, they have this notion of generator, okay? And so property-based tests require random input data, but there's no random data, right? You have to sample it from some distribution. You have to have some mechanism of generating randomness. So you could sample from a uniform distribution, maybe you sample from Gaussian distribution. And it turns out that von Neumann was aware of this in 1947. He actually did the first matrix operations with random matrices, and he was trying to prove that some of his linear algebra decompositions were working, and actually found that based on what distributions he used for the matrix elements, you would get vastly different properties of the algorithms. And so that is why in property-based testing, you need to have some control over your generators. Okay, and so libraries for property-based testing will have all sorts of options. Okay. And so in the vocabulary of property-based testing, the next idea is shrinking. And so what happens with property-based tests, maybe that generated some huge random data, and then at the end, it prints the whole thing, and you're just overwhelmed by the output. And you're like, oh man, like this is not helpful to me, right? I need some way to figure out why this failed on a more minimal test case. And so these libraries, when they find a failing case, what they will try to do is make them more intelligible to you. And so there are a few shrinking techniques. So for instance, if I generated a random array of floating point values, I might call stood round on all of them and then rerun that test. And if it still fails, that'll be easier for a human being to parse and then go and fix. Sometimes they'll split a list in half. So if you had a vector of length 8, you might try to find a counterexample on a vector of length 4. Or you might try and like make these big numbers smaller numbers. Okay. And this is where you start to really need library support for property-based testing. Google test is great for just generating a little bit of random data, but when Google test fails, it fails, right? It doesn't go, I'm going to fail, but not tell you about it and try and find an easier counterexample. And so I used this program called Rapid Check, which is designed for that. And so here is a piece of code which doesn't initialize a dot product, doesn't initialize the S, and then does a dot product on it. And then this is the rapid check syntax. It said let's find out if the vector is symmetric in its arguments. And then I did this, and then it said it's falsifiable after one test with two vectors of length 0. Right? That's that's pretty easy, right? You're like, oh no, like I should have got 0 because the dot product of two empty lists is 0. Well, maybe that's true. I don't know. Maybe it's undefined, but sorry guys. But it still failed, right? Like even if it's even if we have some sort of like reason to reject that case, it failed, and it just pulled off this completely random thing. And then it says, here's this token, which you can then put on your command line and reproduce this. Okay. And so, you know, that was a pretty trivial case. But I think what people really want to know is, does it detect real bugs? And so I've been setting myself a chaotic quest, writing a single class in C++ that doesn't have bugs. I know it's impossible, but I tried it. Okay, so I did a polynomial class. Okay, and so here was my first try at a polynomial. I said, okay, you're going to send me a list of coefficients, and then I'm going to look at the back, and I'm going to prune this down so that all the 0 elements on the back are no longer there, because I want a polynomial of degree n to actually be a polynomial of degree n, not, you know, a quadratic with a 0, you know, parabola term. Okay, and I put this into rabbit check, and it segfaulted immediately. So can anybody tell why this segfaults immediately? What's that? Huh? I'm sorry. It doesn't work for empty. That's exactly right. So the first thing it does is it goes, well, c dot back on an empty vector segfaults. And so I was screwed. All I had to do was switch the order of these two. Right? I could do c dot size better than 1, and then, right, because you get lazy evaluation. So, yep, correct. And then I did another one, and this one was super insidious. This one was really hard. So this is where I commuted the roots. Okay, so in the constructor, I take this list of coefficients and I move them into this vector. And then there's an algorithm called finding the eigenvalues of the companion matrix that gets you the roots of a polynomial. So you form this matrix, and then you initialize it to minus c of I over c dot back. So basically, you're normalizing that polynomial, and all those eigenvalues are the roots. Okay. This one, the crazy thing about this one is it passed like 40 times. I ran this test 40 times, and it passed every single one. But can anybody see what actually happened here that made it fail? So I actually ruled that case out in the constructor, because I'm saying if it's 0, I'm going to pop the back. And so I got that case taken care of. It's a trick question. You can't see. It's in this library. It's in the eigen library. Eigen does not initialize its matrices. You just get a random whatever. Turned out for 40 unit tests, for 40 calls to this unit test, I managed to get a malloc region, which was all zeros. And then on the 41st, it reused some, like, the same memory region, and it failed. And so here's what I actually had to do. I had to pipe in, I have to use this piping syntax to initialize it to 0. It's crazy. Like, how do you know? Like, you know, who is able to like see through their entire dependency stack like that, and then figure out just based on first principles what's actually going to happen? Yeah. Uh, yeah, so I actually have that here. Let's see, here's my polynomial test. Basically, like I generate an arbitrary random vector. And if we go down, let's see. Okay, somebody's got to tell Microsoft about this. I have eigen on my syspath, okay, but it's blacking this out. But actually what you do is you actually have to take the product of all the roots and then show that it's the very close to the I think the constant term, or you sum all the roots and then it's a negative one. Yeah, turns out, yeah, exactly. So that's the test hardness here. Sorry, it's grayed out. Maybe I'll just delete this for now. Fatia just told me to use Clang D rather than this Microsoft stuff. I'm not the only one that wants a flame war tonight. Yeah, that's right. Yeah, exactly. So anyway, I think because of what I do at my job, I have a lot of ability to use property-based testing. But I've talked to a lot of people and they seem to think that their code has no properties. And I would just encourage you to read this book by Fred Hebert. I didn't see a way to property test any of his examples before reading it. And then afterward, it was very natural. He had lots of stuff that was like web-based property tests. He had like a lot of database related property tests. Really cool stuff, a completely different set of examples than what I had here. But nonetheless, I think, ultimately there are no panaceas here. I still can't figure out how to property test images I render. So this is something that's actually been a big pain point for me. Like I've got a lot of code that's generating images, and it's very important that those images are correct. However, like what do I do? Right? I've got some like compressed image format. Like, I have some belief about what it should kind of look like, right? But I can't like look at them. So anyway. So another problem that I had with property-based testing is that the libraries tend to discover unsolved and unsolvable problems, right? So if in my polynomial class, I randomly generated x to the 5,000 as my polynomial, and then I put in 10 to the 300, it's going to overflow, which is very hard to like catch in a very generic way, right? But it's not super helpful. We know that for most inputs on floating point data, even multiplication doesn't work that well, right? Most inputs overflow for random bit patterns. And so this is not helpful. You're just telling us like human beings aren't very smart. I know that. So, but to conclude, I'm too dumb and lazy to use weak ideas, right? This whole grunt out unmotivated test case, it's just a weak proxy for my code probably work. And so I would encourage you all to fill your mental space with powerful abstractions. And I'd like to thank Chris, who helped me use Conan, because I had all these packages. I had Google Test, I had Rapid Check, and Eigen and Boost all in one thing. And I was just getting overwhelmed managing them all. And he was like, no, just use Conan and all. And he helped me out with that. So, hey, thanks, man. I actually wouldn't have been able to give this talk at all or actually have any code that worked associated with it. And also, I'd like to just thank my coworker, Prim Scheller, and Richard Powell for going over these slides before I get them. So anyway, thank you very much. Drager, I'm worried.
Hello? What is the development time of example-based tests compared to the property-based tests? How long does it take to write your scripts versus like hard-coded numbers?
Good. So this is a great question. I actually have come to the opinion that you shouldn't start by writing a property-based test. And the reason is it just feels like too high level of an abstraction when I'm just trying to feel something out, right? Like if I'm testing a polynomial, I want to do like x plus 1, right? And I just want to be done with it because I can just keep that in my head. It's going to do the same thing every time. And then as I'm like, oh, okay, I think this code actually works, then I go to the property-based test. I don't think, honestly, it's taking me that much time to do the property-based test versus the standard testing paradigm. But what I will say is that if you start property testing too early, you're just going to get kind of overwhelmed. Max?
So at the beginning, you went over a couple bad things that happen often with unit tests. One of them being they fail randomly. The other one is that they take a long time.
Yeah.
Pretty much said, well, failing randomly, that's a feature, not a bug. And then for it taking a long time, that's something that I'm wondering. Cause like, how do you figure out how long you should do it for?
Yes.
That's like assuming you're running
Yes.
it in CI, right? So
Yeah.
it's like you don't want your CI to be slow.
So
Yeah,
I have a story for you. We got a new coworker, and he got my unit tests and he ran them, and he wrote me a Slack message. He was like, I just ran your unit tests and it just instantly said return 0 success. And I was like, yeah, I ran over 1 million tests in that time. Right? So look at this. Let's go back to this example. No, you didn't do that. So like let's go back to this example. Let's see if I can find this for sign. Right? Okay, every time you run this, you get novel information, right? Because you're getting a new thing. And then you evaluate sign once, twice. Hopefully the compiler will do like some common sub-expression elimination here, but 3 times. That's like 15 nanoseconds of computation right there. And you only need to run this once, right? Because if you want to run it 1 billion times, you do this Google test where you just repeat it as many times as you want. So in CI, you only need to write this once. Yeah, this fixes that. Yeah. Well, yeah, so so you can run the thing with example-based testing that I see people do a lot is they go, okay, here is like, let's say you had stood sign. You go, let's go from -1 to 1 in increments of 1e minus 15, right? Because we have to test them all, right? We don't know anything about this. And therefore, we're just going to keep on doing that. And then all of a sudden you're at 1e 15 times 5 nanoseconds, which is a very long running test. But if you're like, every time I get novel information, right, I can use that time period to amortize the cost of these tests.
Effectively, what you're doing is some kind of random testing. What about corner cases that will appear like with probability 0?
Almost 0.
So yes, there are. Yeah, I think this kind of alludes to it gets to the same idea, which is that property-based testing does have this problem where you probe what are ostensibly valid inputs, but you leave the set of representable outputs, right? This is actually very common, and you have to kind of work with your generators in the property-based testing framework to actually constrain the valid inputs somewhat so that you don't leave the space of outputs. But, you know, ultimately, like you're trying, when you do example-based tests, everything that you do is in your mental model, right? But that's not how code fails, right? Code fails by things occurring outside your mental model of its correct operation. And so with property-based testing, you're pushing outside your mental model. You're sometimes going into regions where it's annoying. That is absolutely true. But I think that from my experience, as long as I can play with that generator a little bit and constrain the distribution of random inputs in such a way that I can feel confident, then that tends to not happen so much. And also you can also test for these sorts of things, right? Like if you overflow, you just go not a failure. Yeah, exactly.
Thank you. This is a really good example of those flags that people often forget when they use Google Test. Assuming your extensive experience with testing technologies, what other packages are there that have unusual and often forgotten flags that people can just enable out of the box to get new problems spot on?
Yes. So turns, I would not call myself an expert in Google Test at all. I actually wrote my own unit test framework in Boost. And one thing that mine does, which is somewhat unique, is that it's completely designed for like numerical analysis. So when the test fails, you get the floating point number, and then you get the hexadecimal floating point representation as well. So that's something. And another thing you can do is you can specify the ULP distance in my unit testing frequency. So if I'm like saying stood sign should be within 3 representable floating point numbers of this number, I can specify 3. And if it goes above that, it will tell me you were 5 ULPs away. Here's the expected value and its hexadecimal representation. Here's the computed value and its hexadecimal representation. And I also had some other things, like I could put a metric on the entirety of the failures by, I actually summed the entire ULP distance for all my tests. So if I made a global change, I could actually put a metric on whether that improved the entire system. So anyway, that's in Boost math tests, if you want to check it out.
Are there commonalities and differences with fuzz testing against PBT? How does it stack up?
With what testing?
Fuzz testing. Fuzzing?
Fuzz testing, yes. Straker actually knows more about that than me, I think, because he's a compiler guy. My understanding of fuzz testing, which is not great, is that it's mainly for untrusted inputs. Is this kind of, I'm gonna give it.
Most people do fuzzing for security, but it could be used to generate input data. The problem with fuzz testing is that it doesn't have the generators that you talk about. So it's usually a fuzz test framework just gives you a bunch of bits. It doesn't like filter out nans out of flows or give you random vector sizes that are like not a quadrillion each time. So they kind of have different focuses. But personally, I think they're the same, like in theory, but in practice, the tools are different, and that makes them like separate tools that you would pick. Yeah.
So one question I have is like pretty much in every example we saw like what's being tested had like a wide contract, right? Every potential input is a valid input to the given algorithm, but like for a complex enough test subject, I feel like does your generator get complex enough for complex subjects that you have to write a test for your generator? Like how does PBT help in those cases?
Yeah, that's a pain, actually. I actually agree. I think that you've hit on a good point that, you know, this is not a panacea, right? The universe of programming is just too big. And so sometimes you just don't have the meat in a computation that you need to define a really good property. I think that the space of computations that could, like, I think that one of the hardest parts of property-based testing is introducing the definition of correct, right? I think this is something that like students also struggle with as well. They think there is some correct thing out there. I don't know what it is, right? Instead, you should go, I define it as this, and then I show that I meet my definition. And And I think if you adopt that mentality, a lot of programs can be improved, even if the reality is more like there could be a lot of things that are correct and maybe it's very ambiguous. That said, it's one of those issues where I feel my heart bleeds for a lot of programmers, right? Because they work. I mean, like I grew up in Idaho, right? I knew a couple of programmers there, and they're like trying to get the potato machine to like, stop when like it gets like, all blocked up. And then there's like no, there's no definition of blocked up, right? There could be a potato or like a rock, you don't know, right? And so a lot of those programs kind of devolve into spaghetti code. And ultimately you hope, right, that if with knowledge and education, you can move the space of things that are spaghetti code and evolve them into like property tested objects. But it's going to take time, right? I don't think human beings are good at programming. I think in 500 years, we're going to be like, wow, these guys. 5 years, yeah. Actually, even 5 years ago, right? Like, I think 10 years ago, I would look at the stuff that I was doing and I was like, oh God, right? This was horrible. And I was uneducated back then, for sure. But I was not uniquely uneducated. So I think, even now, people have gotten much better at programming as a civilization, we've gotten better. And I think we can continue that, right?
So there was a question earlier about edge cases, and I've never done PBT before, but I was wondering, like, is it common to like, so the idea that I had for edge cases is that you could have a few examples for edge cases that you know are there, and then complement that with PBT. So like for your dot product example, if you want whatever the dot product of two empty vectors, whatever that means, but if you want that to be something like 0, you would want to have a specific test for that, and then you could PBT the rest of it. Is that like a common?
Yeah. I mean, that's what I've been doing in my code as well.
Okay, so you have like some examples, and then
you have some examples that you find, like you want to find those examples that you find compelling, right? You're like, this makes me feel like I communicated a lot of information about the correctness of this, right? And that's again one of the kind of the downsides of property-based testing is that like sometimes it's a little bit too abstract, it's too high level, and you want to just say, oh, what is 1 + 1, man? Like,
All right, are any other questions? Okay. Hey, everyone, let's thank Nick.